So this is the second part of my lecture series in polar coordinate system, the polar equation, and the polar curve. So in this video, I'm going to show you how to find the area of a polar region by applying some concepts of integration. So we shall now develop a formula to find the area of a region bounded by a polar curves. So here, we will let f be a continuous function defined on the closed interval alpha beta, and we let r be a region bounded by r equals f of theta, and between two lines, theta sub 1 equals alpha and theta sub 2 equals beta. So here, we will now consider the partition of delta in the form of a sector on the interval theta sub I minus 1 and theta sub I. So this is the sector we are referring to, and this is taken from the region bounded by these two lines, beta, alpha, and r equals f of theta. So this sector, the angle between the lines theta sub I minus 1 and theta sub I is denoted by delta sub I theta, and this is a sector with radius equal to r. And we recall that the area of a sector is defined by 1/2 r squared theta. So in this case, the area of this sector is given by 1/2 r squared delta sub I theta. Again, to find the area of the entire region, so the idea is to use n subintervals. So we will divide the region into infinitely many sectors, and then by using n subintervals, we can express the area as the sum of the measures of n circular sectors defined by A equals 1/2 r sub 1 squared delta sub 1 theta plus 1/2 r sub 2 squared delta sub 2 theta plus 1/2 r sub 3 squared delta sub 3 theta, running until 1/2 r sub n minus 1 squared delta sub n minus 1 theta plus 1/2 r sub n squared delta sub n theta. And expressing this in summation notation, we have the summation of 1/2 r sub I squared delta sub I theta, where I runs from 1 to n. And this gives the best approximation of the area of the entire region in square units. And you will notice that as we take very small norm delta, which means we the angle between these subintervals is very, very small. So that will give us a very large value for n, where n is the number of sectors used. And if n, the number of sectors, is approaching infinity, is very, very large, then delta theta approaches 0. So we have, as n approaches infinity, your delta theta approaches 0. So we can take the limit of this equation. So the area is now defined by the limit of the summation of 1/2 r sub I squared delta sub I theta, where I runs from 1 to n as delta theta approaches infinity, and as delta theta approaches 0 and n approaches infinity. And writing this in integration notation, we have area is defined by 1/2 times the integral of r squared d theta, evaluated from alpha to beta, since the region is defined on the closed interval alpha beta. Okay, so let's have some example. We wish to find the area of the region bounded by r equals 3 cosine 2 theta. If you are following my lecture series, so you can recall that I have already featured this r equals 2 cosine theta 2 theta, and we enumerated some steps to trace the polar curve r equals 3 cosine 2 theta. So you just check out the description box below for the link of that video. So here we get the intercepts, and the intercepts are the points on the angle 0, pi over 2 pi, 3 pi over 2, and 2 pi. And if theta are 0, pi over 2 pi, 3 pi over 2, and 2 pi, so r is equal to 3, negative 3, 3, negative 3, and 3. So we set these points on the polar coordinate paper. We have 3, 0, negative 3 pi over 2. We have 3 pi, negative 3, 3 pi over 2, and 3, 2 pi. So the next thing to do is to find the intercepts. The symmetry, the test for symmetry. So we replace theta by negative theta, and you will notice that after replacing theta by negative theta, it go back to the original given. Therefore, it is symmetric with respect to the polar axis or the line OX. The next, replace theta by pi minus theta. And then if the equation is unchanged, then it is symmetric with respect to the pi over 2 axis and its extension. And you will notice that the equation is symmetric with respect to the pi over 2 axis or extension. By the way, r equals 3 cosine 2 theta is a 4-leaf rows. Again, so we replace theta by pi plus theta. And if the equation is unchanged, then that is symmetric with respect to the pole or the origin. And you will notice that upon replacing theta by pi plus theta and simplifying, it will go back to the original given. So we have r equals 3 cosine 2 theta. Therefore, it is symmetric with respect to the pole or the origin. Okay. So then since these two steps are not good enough to trace the 4-leaf rows, then we add additional points. So we get points in the angles pi over 6, pi over 4, and pi over 3. On this angles, pi over 6, pi over 4, and pi over 3. So if theta is pi over 6, r is 3 halves. If theta is pi over 4, r is 0. And if theta is pi over 3, r is negative 3 halves. And then we plot it here. Okay. And then we trace the behavior of the curve. We smoothly trace the behavior of the curve. Since we have a point here, then we can draw a curve from 0. It will ascend to pi over 6, and it will go down to the pole of pi over 4. Since at pi over 4, your radius vector r is 0. And then you will notice that for every multiples of pi over 4, the radius vector is always equal to 0. So from in 5 pi over 4, we can draw a curve here. So it will look like this. So from 0 pi 5 pi over 4, it will go to 4 pi over 3, and then to 3 pi over 2. And since this is symmetric with respect to the polar axis, we will have an image here. And this will have a reflection here. And since this is symmetric with respect to the pi over 2 axis, these two curves will have a reflection on the right side. And finally, this petal will have a reflection on the left side. And that completes the 4-leaf rows r equals 3 cosine 2 theta. So the next thing to do is to find the area bounded by this region. So we will be looking for the area of this region enclosed by the 4-leaved rows. So here it goes. So the idea is to get a representative region. So I'll be getting this half of the petal. Okay, so this petal is bounded by r equals 3 cosine 2 theta. The lines theta equals 0 and theta equals pi over 4. So, and then we draw the representative sector. So this is the radius vector r, and then delta theta equals d theta. So this is your change in theta. And then the area is defined by 1/2 the integral of r squared d theta, evaluated from theta, alpha to beta, where alpha is 0 and beta is pi over 4. So we set it up. So where r is equal to 3 cosine 2 theta. So you have a equals 1/2 times the integral of the quantity 3 cosine 2 theta squared d theta, evaluated from 0 to pi over 4. So simplifying the integrand, so this is 3 squared, so you got 9 times 1/2, so we'll have 9 halves. The integral of cosine squared 2 theta, d theta, evaluated from 0 to pi over 4. Since we do not have any direct formula to find the integral of cosine squared 2 theta, we use the identity 1/2 plus 1/2 cosine 2 theta. So in this case, cosine squared 2 theta will become 1/2 plus 1/2 cosine 4 theta. And then you copy 9 halves, and then the integral is evaluated from 0 to pi over 4. So integrating, you have 1/2 d theta is 1/2 theta. And then the integral of cosine 4 theta is 1/4 sine 4 theta times 1/2. It will become 1/8 sine 4 theta. And then you copy 9 halves in front. So you have 9 halves times 1/2 theta. That's the integral of 1/2 d theta. And 1/8 sine 4 theta is the integral of 1/2 cosine 4 theta d theta, evaluated from 0 to pi over 4. And then the next thing to do is to replace theta by pi over 4. And then you will have 9 halves times the quantity 1/2 times pi over 4. That's theta, plus 1/8 sine 4 times pi over 4. Then again, replace theta by 0. So you have minus 9 halves, 1/2 theta, that's 0, plus 1/8 sine 4 theta and replace it by 0. So you will notice that sine 4 times pi over 4 is sine pi. One more, sine 4 times pi over 4 is sine pi, and sine pi is 0. And then 1/2 times 0 is 0. And sine 4 times 0 is sine 0, which is also equal to 0. And then the only thing left to do is to simplify this part, and that will equal to 9/2 times 1/2 times pi over 4 is pi over 8, and the area is given by 9 pi over 16 square units. So the area of this particular sub-region is equal to 9 pi over 16. Going back to the entire region, you will notice that the entire region can be divided into 8 sub-regions, namely A1, A2, A3, A4, A5, A6, A7, and A8. So the total area is equal to 8 times the area of this subregion. So that's 8 times 9 pi over 16. And finally, we have the area enclosed by the 4 leaf rows r equals 3 cosine 2 theta is 9 pi over 2 square units. All right, next. So we find the area of the region bounded by r equals 2 plus 2 sine theta. Again, the step-by-step procedure in tracing the limason, r equals 2 plus 2 sine theta, is featured in my previous video. The link is written in the description box. Okay, and we generated these points. You can use your calculator to verify these points. And then the polar equation is cardioid, facing downward, pointing upward. So we get the area of the region enclosed by the cardioid. Okay, so the area is given by 1/2 times the integral of r squared d theta evaluated from alpha to beta. Okay, so if we use this particular region, okay, the region on the left side, so we choose this as our representative sector. Then this is the radius vector r, and this is the delta theta or d theta. And this region, this half of the region, is defined on the closed interval. This is your theta 1, this is your alpha, and this is your theta 2, this is your beta. So this region is defined on the closed interval pi over 2, 3 pi over 2, because at 3 pi over 2, the radius vector is 0. Okay. So we have alpha is pi over 2 and beta is 3 pi over 2. Now, the area using this particular region, so the area is evaluated from pi over 2 to 3 pi over 2. So we have A equals 1/2 times the integral of 2 plus 2 sine theta square d theta evaluated from from pi over 2 to 3 pi over 2. Now, say we want to use the region on the right side. Okay. So this is the representative sector, and this is your delta theta, which is equal to d theta, and this is the radius vector r. So in this case, the region is now defined on the interval. You start from here, so you do the counterclockwise direction. So you start here, going to pi over 2. So you start at this point, and will terminate at pi over 2. So we have, this is the region is defined on the closed interval, negative pi over 2, that's 3 pi over 2, negative pi over 2 to pi over 2. So we are measuring it in counterclockwise direction. So we have theta is pi over 2 and beta is negative pi over 2. This is the lower limit, this is the upper limit. So this equation can also be written of this form. Area equals 1/2 times the integral of 2 plus 2 sine theta squared d theta evaluated from negative pi over 2 to pi over 2. Okay, then you only choose between these two, because if you evaluate this, the result will still be equal to this one. And do not forget that if you use this portion of the region, so the total area is equal to 2 times the area of this subregion. So we find the area. We will be using the region on the right side. Okay, so the area is equal to, the total area is equal to 2 times 1/2, because the area of this particular region is the same area on this particular region. So that's 2 times 1/2 integral of 2 plus 2 sine theta squared d theta evaluated from negative pi over 2 to pi over 2. So simplifying, so 2 times 1/2 is 1, and then we just expand this. So 2 plus 2 sine theta square is equal to 4. The square of the first 4, twice the product of the first and the second. So 2 times 2 is 4 times 2, that's 8 sine theta, plus the square of the second 4 sine squared theta d theta. And then simplifying further, you can just replace sine squared theta by 1/2 minus 1/2 cosine 2 theta, and that will lead us to 4 plus 8 sine theta plus 4 times 1/2 minus 1/2 cosine 2 theta. And simplifying further, you will have 4 plus 8 sine theta. 4 times 1/2 is 2. And then 4 times negative 1/2 is negative 2. Then you copy cosine 2 theta d theta. And then you can combine 4 plus 2, and that will become 6 plus 8 sine theta minus 2 cosine 2 theta d theta. And we are now ready to evaluate the definite integral. So integrating 6 d theta is 6 theta, 8 sine theta, the integral is negative 8 cosine theta, and the integral of this is negative sine 2 theta. So you'll have 6 theta, that's the integral of 6 d theta, minus 8 cosine theta, that's the integral of 8 sine theta d theta, minus sine 2 theta, that's the integral of negative 2 cosine 2 theta d theta. Cosine 2 theta d theta, the integral is 1/2 sine 2 theta times negative 2, that is negative 1. And then we are ready to replace theta by negative pi over 2 and pi over 2. Evaluating the definite integral, we have 6 times pi over 2 minus 8 cosine pi over 2 minus sine 2 times pi over 2, and then replace theta by negative pi over 2. And then minus 6 times negative pi over 2 minus 8 cosine negative pi over 2 minus sine 2 times negative pi over 2. So simplifying, you all know that cosine pi over 2 is 0. And 2 times pi over 2 is pi. Sine pi is also 0. And then again, cosine negative pi over 2 is still 0. And 2 times negative pi over 2 is negative pi. Sine of negative pi is still 0. So the only thing left to do is this and this. So you have 6 times pi over 2. That's 3 pi. Okay, and then minus 6 times negative pi over 2 is negative 3 pi. So adding this 2, you got 6 pi square units. So this is the total area of the region enclosed by the cardioid r equals 2 plus 2 sine theta. Okay, for the third example, we will be working on the lemniscate r squared equals 4 cosine 2 theta. Again, this has been featured on my previous video, the step-by-step procedure on how to trace the polar curve r squared equals 4 cosine 2 theta. So we first get the intercepts. So again, this is r squared equals 4 cosine 2 theta. We only get the value of r equals to the square root of cosine 2 theta. So replace theta by 0, pi over 2 pi, 3 pi over 2, and 2 pi, and we get these points. Again, do not forget why this is infinity, because 2 times pi over 2 is pi, cosine pi is negative 1, and the square root of a negative number do not exist. Okay, same with 3 pi over 2. In every multiples of pi over 2, the radius vector r is undefined. And then we test for the symmetry and then plot these points, of course. So you have 2, 0, and then 2 pi, and then 0, 2, 2 pi. So we only have these 2 points. Again, for the test of symmetry, we replace theta by negative theta, and you will notice that it will go back to the original given. Therefore, the lemniscate is symmetric with respect to the polar axis or the line OX. And then replace theta by pi minus theta. And again, simplifying, it will go back to the original given. R squared equals 4 cosine 2 theta. And then finally, we replace theta by pi minus theta. And then you will notice that it will go back to the original given. Okay, R squared equals 4 cosine 2 theta. And therefore, it is symmetric with respect to the pole or the origin. And then since these 2 points are not good enough to trace the lemniscate, and then we add additional points. So we replace theta by pi over 6. So cosine 2 times pi over 6 is cosine pi over 3, and cosine pi over 3 is 1/2. The square root of 1/2 is square root of 2 over 2 times 2. So you have square root of 2. And then for pi over 4, cosine 2 times pi over 4 is pi over 2, and cosine pi over 2 is 0. Square root of 0 is 0 times 2 is still 0. And then for pi over 3, cosine 2 times pi over 3 is cosine 2 pi over 3, and 2 pi over 3 is on the negative x-axis. So it's in between the angle pi over 2 and pi, and the cosine function on that particular angle is negative. The square root of a negative number do not exist, so you have pi. So which means for every angles multiple of pi over 3, then the radius vector r is undefined. So we trace these points on the polar coordinate paper. So this point is your square root of 2 pi over 6, and pi over 4 is 0. So this is 0 pi over 4. And then again, you cannot place this on the polar coordinate paper since the radius vector r in pi over 3 do not exist. And then the next thing to do is to smoothly trace the behavior of the curve. So let's start here. So this is 0. Then part of the lemniscate will be drawn from this point going to pi over 6, and then down to the pole of pi over 4. So you have this part of the equation. And again, since this is symmetric with respect to the the polar axis or the line OX, then this part of the lemniscate will have a reflection over this line. So you have, okay, and again, this lemniscate is symmetric with respect to the pi over 2 axis and its extension. So you have this. Okay, this is pi over 2 axis, and then you reflect it over this line. So you have completed the lemniscate r squared equals 4 cosine 2 theta, and then the next thing to do is to find the area bounded by this region. Okay, so what we are going to do is to get an interval. Say we want to do it in negative pi over 4 to pi over 4. So this is your 7 pi over 4. 7 pi over 4 is the same as negative pi over 4. So this is your negative pi over 4, and we will be measuring it in counterclockwise direction. So you will terminate at pi over 4 because at pi over 4, the radius vector is 0. So if you are doing it in the interval negative pi over 4 to pi over 4, so this is your A1, and this is your A2. So the total area is equal to twice the area of A1. So you have alpha is negative pi over 4 and beta is pi over 4. So the integral would have been equal to, the total area is 2 times 1/2 times the integral of 4 cosine 2 theta d theta. So since from the formula, that's already r squared, and the equation of our polar curve is r squared equals 4 cosine 2 theta. So you only have 4 cosine 2 theta d theta. And then if you want to do it at 0 pi over 4, so this is your 0, and this is your pi over 4. So we are dividing the entire region into 4 equal subregions, namely A1, A2, A3, A4. So you have alpha equals 0, this angle, and beta is pi over 4. So we are evaluating the limit from 0 to pi over 4. And the total area is given by 4 times the area of this subregion. So 4 times 1/2 times the integral of 4 cosine 2 theta d theta evaluated from 0 to pi over 4. And simplifying, we have 4 times 1/2 is 2 times 4, that becomes 8. One more. It's 4 times 1/2 times 4, that's 8 times the integral of cosine 2 theta d theta. And then integrating this, you have 8 times the integral of cosine 2 theta is 1/2 sine 2 theta evaluated from 0 to pi over 4. And 8 times 1/2 is 4 sine 2 theta from evaluated from 0 to pi over 4. And then we now replace theta by pi over 4 and then by 0. So you have 4 sine 2 times theta, that's pi over 4, minus 4 sine 2 times 0. And we all know that sine 2 times 0 is sine 0, which is equal to 0. And then you have sine 2 times pi over 4 is pi over 2, and sine pi over 2 is 1. So you only have 4 times 1 for the first term. And then the total area is equal to 4 square units. So that's it for now. And you keep on tuning into my channel for more videos on integral calculus.